All right, today we're talking about something really cool. It's some of the most valuable and totally invisible real estate in our entire solar system. We're talking about the 5 Lagrange. It's being pulled and pushed by gravity all over the place. So where on Earth, or, off Earth, do you park something like a satellite or a telescope? How do you keep it from just drifting away or having to burn tons and tons of precious fuel just to stay put? Well, it turns out the answer is in a few very special locations. And the solution is it's so elegant. In any system with 2 big objects, like our Sun and the Earth, there are exactly 5 spots where all the gravitational forces just perfectly balance each other out. And that's what these are, orbital anchors. Think of them like invisible parking spots floating out there in the cosmic ocean. So, what's the secret sauce here? What makes these orbital anchors actually work? Well, it all goes back to this brilliant bit of celestial mechanics figured out by a mathematician named Joseph Louis Lagrange way back in the 18th century. Okay, so what is a Lagrange point? It's basically a gravitational sweet spot. It's this one specific place where the pull from the Sun and the pull from the Earth and the force that's trying to fling an object outward as it orbits, they all just cancel each other out. It's this perfect point of equilibrium where something can just hang out with almost no effort at all. Picture this. It's like a cosmic tug of war. You've got the Sun's massive gravity pulling a satellite one way, then you have the Earth pulling it another way. And at the same time, the satellite's own momentum is trying to fling it out into space. At a Lagrange point, all those forces are in a perfect deadlock. The rope doesn't move. Everything is just held there in this delicate but incredibly useful harmony. All right, so let's take a little tour of these 5 points. We're going to start with what we call the unstable trio. Now, these 3, they all lie on a straight line that connects the Sun and the Earth, and you'll see why they require a pretty careful touch to use. First up, we've got Lagrange point 1, or L1 for short. This spot is basically the perfect perch for a solar observatory. It gives you an uninterrupted front row seat to our star. See, L1 is parked right between the Earth and the Sun, so spacecraft like SOHO get this constant, unbroken view of everything the Sun is doing. And that's super important for warning us about things like solar flares and space weather. The catch? It's what we call an unstable point. It needs really precise navigation and these little, regular burns of fuel to stay in place. That whole process is called station keeping. Okay, next up is L2. This one's on the far side of the Earth from the Sun. And this is the premium spot for peering deep into the universe. You've definitely heard of the most famous resident here, the James Webb Space Telescope. From L2, the Earth, the Sun, and the Moon are all in the same direction. This means the telescope's giant sunshield can block out all of their heat and light at once. That keeps the instruments incredibly cold, which you absolutely need for infrared astronomy. And just like L1, L2 is unstable, so it also needs to do that station-keeping thing to stick around. All right, our third stop is the mysterious, kind of elusive L3. This is a point that has really captured the imagination of sci-fi writers for, decades. So L3 is always hidden directly behind the Sun from our point of view. That's why it became this popular idea in science fiction for a secret counter-Earth. But in reality, the Sun's gravity just makes it super unstable. Plus, trying to communicate through the Sun? Yeah, that's pretty much impossible. So for now, L3 is just sitting there, empty. Okay, so this is really the key thing to get: stability. The points we just talked about, L1, L2, and L3, they're like trying to balance a marble on the very top of a hill. The slightest nudge and, whoops, it rolls away. That's why they need constant corrections. But our next 2 stops, L4 and L5, are totally different. They're like putting that marble inside a bowl. If you push it, it just rolls right back to the bottom. They are actually truly stable. So, let's go check out these stable points now. You can think of them as the gravitational valleys of our solar system. Welcome to L4 and L5. If L1 and L2 are these super high-tech precision observatories, then L4 and L5, they're more like cosmic campgrounds. They're these natural gathering spots for pretty much anything that happens to wander by. Geometrically, L4 and L5 form these perfect equilateral triangles with the Sun and the Earth. One of them, L4, leads the Earth in its orbit by 60 degrees, and the other, L5, follows behind by 60 degrees. Because they're so stable, they act like these huge gravitational wells. Over billions of years, they've collected clouds of space dust and even asteroids. We call these Trojan asteroids, and they actually share Earth's orbit, just locked in place by gravity. So there you have it. Our grand tour of the Lagrange points is complete. But the big question is, so what? Why do they actually matter? What makes these 5 little spots in space so critical for the future of how we explore everything out there?
Well, for one, they give us that front row seat to the cosmos. And just as importantly, they save an enormous amount of fuel, which means our missions can last way, way longer. And when we look to the future, those super stable L4 and L5 points, they're seen as the perfect spots for future space stations or supply depots. They could literally be our gateways to the rest of the solar system.
Really, it all comes down to this one simple idea. Lagrange points are these amazing places where we can make the universe's own laws of gravity work for us instead of against us. They are the true sweet spots out there, letting us anchor ourselves in the cosmos and explore in ways that would be pretty much impossible otherwise. These 5 orbital anchors have already completely transformed how we see the universe, from looking at our own star to peering back at the dawn of time itself. So as we keep pushing further out there, the real question is, what are we going to use them for next? What new discoveries will they help us unlock?